All right, go ahead.
All right, let's get started. Good morning, everyone. Thank you, Ryan, for the introduction. And as Ryan mentioned, I'm going to give an update on looking at if we can sense the compaction layer using the electrical conductivity method. So just to kind of give a bit of a rationale that why even we bother. So the compaction can be one of the yield limiting factors, so that's why it's worth exploring and see if we can propose like a variable rate tillage map or some sort of a management strategy so that we can break that hard pan, and also so that's going to facilitate the plant growth obviously, and also it will have an impact on the yield. So the compaction could be a function of various soil variables. The most important one of those is the bulk density. That if obviously if the bulk density changes, so that means there is either it is a loose soil or it is a compacted soil, because the air particles will be replaced with the soil particles and whatnot. So just to kind of give a very brief overview, I know all of you know the composition of the soil, and then when the compaction happens, and obviously those air particles are replaced and they kind of make their way out and the soil particles get compacted, and void ratio, which is the ratio of the air and the water in the soil, that kind of changes and it causes the compaction. And bulk density, as I mentioned, is an important factor. So now if you look at this chart, so the bulk density, ideal bulk density in this chart for the plant growth, that varies for different soil types. It can vary from 1.1 to 1.6, so that's more sort of an ideal range. But if our numbers are higher than that, we are potentially looking into compaction, depending on what is the soil type. So now with that, obviously the compaction can have an impact on the root growth, that the root penetration will be an issue, and it can cause a bit of a growth problem, and that will be reflected in the yield. Not only that, so it can also have a bit of a water problem, that the water will not infiltrate or percolate through the soil, and then it will end up standing. If it is a slopey field, then we might get into some level of erosion because the water has to find its way to go out. So that could be another potential problem related to compaction. So now just to kind of give, so in potato production, so there is a lot of machinery movement. So when it comes to the tillage and harvest and also picking the potatoes, transporting them, so so obviously that can cause the compaction situation within the fields, and the compaction could be anywhere in the soil layer. It could be in the top 6 inches, 12 inches, 50 inches, wherever. But what we figured and what we are looking into, that anything below 40 centimeter we cannot manage. We can't do anything about it. So that means if we can focus on the top 40 centimeters and come up with a plan to break that hard pan, so that's the way to go. That's the practical solution we are proposing. So the objective or the goal of this project was to look into the electrical conductivity, and many of you might be using the SWOT mapping for different reasons. So it's the exact same principle. It creates the magnetic field in the soil and kind of correlated with many variables. And then based on that, so we want to develop a management zone and variable rate tillage plans, and that will ultimately help with the conservation and improve the profitability. So the specific objectives of this project are to look at the potential of EMI to detect the compaction within potato fields in top 40 centimeter. As I indicated earlier, anything lower than that, so we don't have the equipment to break the hard pan, so we need to be a little bit practical here.
Aitazaz, would it be possible for you maybe to just speak from the other side of the screen?
Sure.
That would be great. Thanks.
Oh. So then the second objective is not only to, because the conductivity sensor we have at UPEI, but SWOT mapping is more commercial option available, and it works on the same principle. And then the idea is to check on the SWOT map and see if we can detect the compaction. So then whatever we are proposing, so that will be a commercial option available for the grower, so it doesn't sit with UPEI. And then thirdly, the idea is to delineate the management zone for a very, very tillage. Like in certain part of the fields you're encountering are dealing with the compaction, you might want to go a little bit deeper than the grower standard tillage to break that hard band to be a little bit more practical and profitable. Some images from the field, so we did extensive sampling. We had few fields, about 10 to 12 samples. We determined where the compaction was. We had the moisture content recorded. We had the soil temperature recorded. We also had the penetrometer to go with it, so that and also the conductivity data. So there are some more images, data collection within the field, and this yellow tube, so it can take the point measurement where we are looking at the compaction. We can also record the conductivity at the same point, so that we can have an established relationship with that. Few more images during data collection, and then so this is the bulk density we calculated at the lab at the university for the samples we have, just to kind of give an understanding. As I said, it's exact same principle as the SWOT maps. So that yellow tube, so it has two transmitters, one receiver. It creates the magnetic field, and that magnetic field is reflected and kind of correlated with other, and it can sense 3 meter below the soil surface. But what we are interested in is that since we are focusing on the top 40 centimeter, we would like to see what is the response in the top 40 centimeters so that our estimations are accurate. So some results from this study. So these are the soil temperature differences at various depths. So at 20 centimeter, 40, 60, and then you can see the trends are as you go deeper, the temperature increases in the soil. And then this is the moisture content at different depths as we go. So we recorded using the the time domain reflectometry sensor, and also we had the soil samples which we determined the moisture content in the lab as well by over drying method. And you can see as you go deep, so the moisture increases. So the next one is the bulk density. So this is an important slide to look at. So at various depths, so for example in here, let's focus on this sample. So at 20 centimeter, so you're looking at 1.5. You go 40, so you're looking at around 1.7 or 1.65, whatever. And here you're below 1.75. So that kind of gives an indication that for this particular sampling point, so there is some level of compaction going on here. Now the question is whether it is manageable or not. So that's why we want to focus in the top 40 centimeter or 12 inches to see, 15 inches to see what we can do about it. So for the second field, the similar trend, so it ranges from 1.25 and kind of 1.75 with the, so for example, in these three samples, not a whole lot of compaction going on because the values were really high. So these are the penetrometer readings with the handheld, and you can see with the handheld meter resistance to penetration. So, and again in this case we had 6 inches, 12 inches, 18 inches, 30 inches below the soil surface. And the idea was to look at how much is the resistance and whether that translates and reflects the compaction. So if you look at it, so as we go deep, so we need more force to kind of penetrate through the soil, so which is up. And now with this, based on the bulk density, based on this penetrometer reading, so we will be establishing over the next couple of years that what are the magic numbers. What kind of resistance value is when we call it is compacted. And what is the limit, or say, I'm just making up here, maybe from 50 to 100, we say no, it's not compacted, or mildly compacted. Anything over 200, I'm just making up. Maybe it is highly compacted or severely compacted. So those will be the values which we will be determining as we go, so that we can have a bit of a sense how the compaction is doing. So then after that, so we had these curves developed. So this is the line for 24 inches. 12 inches, 6 inches, and you can see in any case, so there was a good correlation when it comes to the conductivity and the resistance. That showed us a bit of a potential that how we can use that data to determine the compaction. Some more results on the different variables with the conductivity. So again, good relationships, not very highly significant, but a good start. And then eventually we transported all the data in GIS to look at the compaction layers visually so that we can kind of see what's going on in terms of compaction. So on the right hand side, so this is the compaction layer in the top 30 centimeter. And then the red area, so these are the areas which seem to be highly compacted, and the green areas are okay, yellow are sort of in the middle. When you go what is this? I can't read. So 50 centimeter below, so you can see the trend is slightly different because it's not consistent as it was in the top layer. And then for the same field, when we go more deep, 60 centimeter, 120 centimeter, 1 meter below the soil surface, so you again see how it correlates with the conductivity and how the trends are looking. Another field to look at the compaction, same sort of strategy. Compaction was variable, so it wasn't so, and like any other agriculture property. So again, some more maps on the compaction, few more to conductivity. So now one more thing with the SWOT maps, we can get in the raw data, we get two levels of conductivity, shallow conductivity and deep conductivity. So in the next stage, we are thinking if we have two fractions, deep and shallow, and we try out differently and see if we can only use one fraction for detection of the compaction. In that way, growers are doing SWOT mapping anyway. If we can utilize the same data with the shallow conductivity or deep conductivity and kind of correlate that with the compaction, that's the way to go. So another field with the, so now at the end of the day, whatever we do, it has to make sense, economic sense, so that we can pay the bills for the growers can pay the bills. So then obviously from the fields we selected, and those growers have half of the field or middle of the field subsoil, and on the side it wasn't subsoil. In other field it was subsoil on the sides and the middle was. So it was basically treatment versus non-treatment. And it was all done based on their knowledge of the field. And then we end up picking the plots, and we did the manual digs and recorded all the data and collected the yield and quality and payout and marketable yield analysis for all of that. So this is the site number 1. If you look at where we had the subsoiling done, so the yield was about 30 hundredweight higher compared to the where there was no subsoiling, or it was the check. Okay. So now also when we look at the total payable, it was higher in the subsoil, and then also if you look at this good tubers, so they were higher. Okay. So this was the trend we found, and we collected that using the manual digs in the subsoil and non-subsoil areas. So for the second field, similar trend was observed. So the yield was higher by 25 to 30 hundredweight, where the subsoiling was done, and the total payable was higher. Defects were found to be higher in this case, but the good tubers were also higher. So, but in general, trend was that the marketable was high. So now when we look at those numbers and do some statistical digging, so although the yield was higher, but it was non-significantly different. And the reason for that would be that in each field we had about 9 to 15 samples somewhere, which is a small sample size to establish any statistical correlation. But now Andrew, as Ryan introduced, Andrew is a master's student, started with me in January. So he's going to be building on this project and kind of having more investigations and thought process into it so that we can look into statistical. And we will be increasing the sample size on this field while we are expanding. And Ryan will be helping us with the field collection and reaching out to you guys for the fields. So in 2022, so we again had 2 fields. So if you look at the yield trend, so in this, the trend was a little bit opposite. So where the checkpoint, which are the grower standard, they had the higher yield compared to the subsoiled areas. And the similar trend for the total comparison, and then the marketable yield was higher and non-significantly different specific gravity. So this trend was opposite, and the reason could be that the compaction layer was deeper than where the grower operated the tillage equipment. So that's just an assumption. It could be the reason. The other possible reasons could be the field topography playing the role. One field was flat, the other wasn't, or something like that. So we are still looking into the reasoning to establish what could be the possible cause of that. But the second field in the year 2022 showed exact same trend as field 1 and field 2. So higher yield, higher marketable potatoes, total payables, and so 3 out of 4 fields where the subsoiling was done, it showed higher potential for the yield. And one, again, there could be the reasons for that.
So your treatment is just a subsoiling?
Subsoil, yeah.
Subsoil.
It was done according to where, like, I went in with the penetrometer and went down to find the plow pan in each field. So it was dependent on where the plow pan was, and then they would go 2 to 3 inches under the plow pan. So one of the fields, I think the plow pan was at 10 inches, so we would have done it at about 12, 13.
That wasn't in Surrey.
What's that?
That wasn't in Surrey.
No. And then another one, the plow pan was at more like at 12 inches, so then he did it at about 15. So.
And then just to kind of summarize the yield data, so we had the promising results that if we break the hard band, so there is a potential and promise to increase the yield. And then, but with these particular data side, we were not able to establish any statistical significance, and the reason I gave you was the sample size, but we will be increasing the sample size to come up with those statistical significance. Just to kind of briefly give this an update, so as Andrew is building on this, and we purchased these 2 softwares, and we will be utilizing these, and these are meant to deal with the compaction, and it will develop the compaction layer and whatnot. So this was one of the field we had, so this is the initial survey, how it looked like. Then the data processing happens with this software, so that's the initial raw data. Then that shows the variation with the high and low values within the field. Then there is a bit of cleaning to get rid of undesired data. And then this is how it creates the surface. And the idea is that, so this is the model which you will, so this is the conductivity, how it changes within the soil profile. So for example, this is for 30 centimeter, and then this is for 60 centimeter. You can see the surface changes. The values changes, so it's not the same, and it could be because of the texture, moisture content, compaction, so all in integration playing a role for that kind of variability. If we go deep, the trend also changes, so at 2 meter and 2.6 meter. So you can see, so the idea for our study is to fraction off like this and show that there is the compaction, and again, kind of translating that into practicality. Yes, there is a compaction, but we can do a little bit. Is that manageable or not?
So will doing it this way give you a truer value? Like if you're going out looking for compaction in the spring or the fall and everything is wet and loose, and what you're using penetrometer will go down easily.
Yeah.
Middle of the summer when it's dry and hard and the soil all tightens up, it's not going to go down very easy.
Yeah. So I think the idea will be that we will be collecting the readings when it is wet and dry so that we get an average response. You're right that the moisture has a role to play, but if we encounter all that variability within the calculation, when it is dry, when it is wet, when it's somewhere in the middle, then I think once we have an average response, we should be able to pick.
So ideally, if you take the same field and scan it multiple times under different conditions, then over time you can correct the response so that then you could do it in the summer when it's easiest to do, when you're doing your other SWOT mapping or doing your other detection, and then you don't have to do it when it's necessarily moist or whatever. And then, as is saying, then he's hoping to use this software to then be able to fraction about how deep is that plow layer, how deep is that compaction layer.
Yeah.
So.
And I think, just to add on Ryan's point, that when we do that over the season multiple times, we can come up with a fraction. So say in a dry scenario, we're getting an average value of 6. In the wet scenario, we're getting an average value of, say, 8 from the same soil. Obviously, that increase in value is caused by the moisture, because the rest all is the same. And it could be the temperature variation somewhat too. So that's the second software, works exactly the same. So it can pick on the noise if the conductivity sensor is close to the electrical lines, or also close to the tractor and machinery. So then it kind of gives you very high value. And then that is an outlier, because that magnetic field is impacted by the machinery. So then we can pick on that, so there is outlier pick. And this is the surface. So for example, this is the compaction layer here. So you can see as it starts, and it kind of gives a bit of a trend. So these are preliminary results, and that kind of shows where the severity of the compaction is happening. And that's what we are hoping to get for potato fields, that if we can have a profile like this, where we can show that in northern part of your field, you're looking at 20 inches below compaction. On eastern side, it is only 10 inches or 8 inches, so that you can come up with a basically site-specific tillage plan to break that hard pan and improve the productivity and growth. So this is again a bit of a 3D model for the data to look at, like how you can go deep, again very preliminary. So the idea came from a gravel pit extension project. This was from Denmark. So they used the conductivity to look into the bore drilling and kind of see where they can extend the site and not. And then when they did their study, obviously they mapped with the EC, then they created those grid maps, and this is the profile how it looks. That in the profile 1, profile 2, and these are the boreholes. And that kind of guided them and advised them like where you're dealing with the severe situations and easy situations and whatnot to make that decision making easier. So we will be doing quite a bit of work using these two software with the additional fields and the fields we have, and obviously we'll be exploring into SWOT data to come up with these kind of profiles for the potato fields. And at the end, I would like to conclude that yes, there was a promising potential for the dual EM and to pick on and sense the compaction layer, and then also the layered response can be used to correlate it with the conductivity. Yield was higher, but non-significantly, but adding more samples and pooling the data together could be an option to go to establish the statistical significance, and we will be doing some more work on that. At the end, I would like to acknowledge Ryan and Morgan for their support during the experimentation. They were involved during the data collection and also yield collection, and the Potato Board for their support to fund this project, and my team for data collection, MyTex, and I would like to acknowledge Andrew. He worked hard last week because these were new softwares and we want to try out and kind of get you guys excited that we are working on it. And thank you, Ryan and Potato Board and all of you for listening.
Thanks, Isaiah.